Quality control of semi-solids, ointments and creams. Quality control plays a crucial role in ensuring the safety, efficacy, and overall quality of ointments and creams used in dermatological applications. In this field, quality control refers to the systematic processes and procedures implemented to monitor and evaluate various aspects of these topical formulations. It involves rigorous testing, analysis, and adherence to established standards to ensure that the final products meet the desired specifications. What dose semisolids mean, and what are they used for? Semisolids dosage forms are products of semisolids consistency and applied to skin or mucous membrane for therapeutic or protective action or cosmetic function. Each of them has unique characteristics and properties that make them suitable for specific applications. Creams. Creams are semi-solid emulsions, typically composed of a water phase and an oil phase. They consist of small droplets of oil dispersed in a water-based matrix. Creams are usually smooth and easily spreadable, with a non-greasy or non-sticky texture. They are commonly used for moisturizing, hydrating, and delivering active ingredients to the skin. Ointments. Ointments are semi-solid preparations primarily composed of a hydrophobic base, such as petrolatum or lanolin. They have a greasy or oily texture and usually do not contain a few amount of water. Ointments are occlusive and provide a barrier on the skin, providing enhanced penetration of active ingredients. Often used for conditions requiring increased moisturization or protection. Gels. Gels are semi-solid formulations consisting of a three-dimensional network of solid particles dispersed in a liquid phase, which is typically water or a water-alcohol mixture. Gels have a unique texture, often described as being jelly-like or viscous. They are known for their cooling and soothing properties and are commonly used for topical applications such as wound healing, acne treatment, or delivering drugs through the skin. What are they used for? Moisturization and hydration of the skin. Sunscreen protection and prevention of sunburn. Acne treatment and prevention. Wound healing and scar reduction. Relief of itching, inflammation, and irritation. Drug delivery through the skin, topical medications. Is there any physical and psychological factors affecting these topical formulations? Several physical and psychological factors influence the efficacy and acceptance of semisolids. For example, physical factors include viscosity, spreadability, texture, stability. These properties can influence the product's ease of application and absorption into the skin and overall user experience. And psychological factors include irritation, alteration of skin membrane or function, visual appearance, tactile sensations. All of these factors can contribute to the overall sensory experience and can impact the product's acceptance and compliance. Raw material quality control. Raw materials refer to the basic substances or components used in the production of semisolids, and they can be classified to 1 active ingredient, API. For example, zinc oxide, paracetamol, etc. 2 inactive materials, excipient. For example, sucrose, starch, etc. And these raw materials will undergo quality control tests to ensure that the ingredients used in the manufacturing process meet the required specifications and standards. These tests help assess the identity, purity, strength, and overall quality of the raw materials. Some common quality control tests for raw materials include 1 loss on drying. In this test, a small sample of the raw material is heated at a specific temperature, typically around 105 degrees C, until a constant weight is achieved. The weight loss observed during heating represents the amount of moisture present in the material. 2 Carl Fisher water content test determines the amount of water present in the raw material by titration and endpoint identification against the sample. By measuring and controlling the moisture content in raw materials, manufacturers can ensure the suitability and stability of the formulation during production and storage. 3 sulfated ash test. In this test, a known quantity of the raw material is ignited at high temperatures in a muffle, typically around 600–800 degrees C. the organic matter present in the material is burnt off, leaving behind the inorganic residue. This residue is then treated with sulfuric acid to convert it into sulfates, and the remaining ash is quantified. The sulfated ash test is important because it provides information about the purity and presence of inorganic impurities in the raw material. These are just a few examples of the quality control tests performed on raw materials. And the specific tests conducted may vary depending on the nature of the raw material and regulatory requirements. The purpose of these tests is to ensure that the raw materials used in the production process meet the necessary quality standards and contribute to the safety, efficacy, and overall quality of the final product.
In-process quality control plays a crucial role in ensuring the production of high-quality ointments and creams. It involves a series of checks and tests conducted at various stages of the manufacturing process to monitor and control the quality of the product. The primary objectives of in-process quality control are to identify and rectify any deviations or abnormalities during production, prevent the occurrence of defects, and maintain consistency in product quality. Factors affecting product characteristics and quality during in-process quality control. 1. Formulations factors. Active pharmaceutical ingredient concentration. The concentration of the active ingredient in the formulation can affect the potency and efficacy of the product. Excipient selection. The choice of excipients, such as emulsifiers, stabilizers, and preservatives, can impact the stability, texture, and overall quality of the product. pH and buffering capacity. The pH of the formulation can affect the stability and compatibility of the ingredients, as well as the skin irritation potential. Viscosity. The viscosity of the formulation can influence the spreadability, ease of application, and drug release characteristics. 2. Process factors. Mixing rate. The speed and intensity of mixing can affect the homogeneity and particle distribution in the formulation. Temperature. The temperature during the manufacturing process can impact the stability, viscosity, and drug release properties of the product. Time. The duration of various processing steps, such as mixing and heating, can influence the final product characteristics. Cooling rate. The rate at which the product is cooled can affect the crystallinity, texture, and stability of the formulation. In-process quality control tests for ointments and creams. Appearance and uniformity, pH testing, active ingredient content, microbial contamination testing, stability testing, texture and consistency, evaluation, homogeneity testing, packaging integrity testing, preservative efficacy testing, skin irritation and sensitization testing.
Finished products. Quality control is the last stage in drug formulation before packaging and labeling. In other words, finished products are the intended form in which drugs are ready to be used and exert their intended effect. We have three main categories: universal tests, specific tests, and performance test. Universal tests. Description. Simple test as it's done by visual examination where we detect changes in color, separation, crystallization, and many other for each type of dosage forms. Identification. Qualitative identification of the active ingredient in the finished dosage form by using one of the following methods: IR spectroscopy or Raman spectroscopy chromatography. Assay. The quantity of drug present in unit weight or volume of ointment is determined by spectrophotometric method, titrimetric method, and microbiological assay. Impurities. Impurities that develop throughout the production process, as well as those that develop during the degradation of the drug substance, should also be evaluated and managed. Specific tests. Viscosity determination. It is possible to measure the viscosity of various topical formulations using a Bookfield viscometer. At 21 degrees Celsius, the tests to be conducted, various RPMs were used to rotate the spindle and every measurement to be done 3 times. Uniformity of weight. Choose 10 filled containers as a sample. Each container should be weighed after being cleaned and dried. Quantitatively empty each container of its contents. The container's other components, including the closure, are kept. Each empty container should be dried before being weighed again. The net weight of the container's contents is the difference between the 2 weights. The average net weight of the contents of the 10 containers is not less than the labeled amount. The net weight of the contents of any single containers is not less than 91% and does not exceed 109% of the labeled amount. Where the labeled amount is 60 grams or less, or not less than 95.5%, and does not exceed 104.5% of the labeled amount, where the labeled is more than 60 grams but does not exceed 150 grams. Test of microbial content. Pseudomonas aeruginosa and Staphylococcus aureus are 2 examples of the microorganisms that could contaminate the preparation. Solutions are created using various preparation sample. Under aseptic conditions, each sample is inoculated into separate volumes of rabbit plasma, where it is then incubated for 1 to 4 hours. The absence of the clot in the incubated mass indicates that there are no microorganisms present. Sterility test. Depending on the dosage form's intended use, we choose either method A, membrane filtration, or method B, direct inoculation. Method A, membrane filtration. Diluted in a sterile solvent such as isopropyl myristate. Aseptically dispense the appropriate amount of product as required. Then allow all the fluid to filter through the membrane. The growth media we use are soybean casein digest medium and clear fluid thioglycolate medium. Method B. Direct inoculation. The inoculated media for a minimum of 14 days. Observe the cultures several times throughout the 14 days of incubation. Further incubation is not required if the test specimen is positive before the required 14-day incubation period. Incubate the test specimen for a minimum of 7 days if the product has been terminally sterilized using a validated moist heat process. Use method B if the ointments or oils are not soluble in isopropyl myristate. No evidence of growth. Passed the test for sterility. Evidence of growth. Retesting is performed with twice number of sample no growth. Passed the test if growth occurs. Failed the test for sterility. Preservative efficacy test. Using the pour plate technique. Solutions of various preparation sample specimens mixed separately with tryptone azolectin tween broth. Each mixture that is incubated receives the addition of microorganism cultures. Throughout specific days, the number of microorganisms in each sample is then counted. Bacteria, not less than 1.0 log reduction from initial 14 and no increase at 28 days. Yeast and mold, no increase at 14 and amp, 28 days. Particle size. Apply a thin layer of the semi-solid to a microscope slide. 50 representative samples should be scanned. None of the 20 particles have a maximum dimension larger than 100 micrometer, while not more than 10 particles have a maximum dimension greater than 50 micrometer. Water content. Low water activity reduces susceptibility to microorganisms, and the water activity test is typically formulation dependent. Antioxidant content. Acceptance standards. The amount of antioxidant required to preserve the product's stability throughout its proposed usage and shelf life. Solubility. The mixture ought to dissolve in 1.7 parts of hot water and 9 parts of water. Alcohol, ether, and chloroform should all be miscible with the contents. pH determination. On application to the skin, avoid causing irritation. pH meter. Glass electrode instrument used in this test. A topical preparation weight of 1 gram is dissolved in 100 milliliters of distilled water and kept for 2 hours. The pH is measured 3 times with the average values being computed. Performance tests. Visual inspection should be smooth and free of solid particles. For aluminum tube, pressure to be applied with a finger. The amount of ointment that comes out the tip is measured to determine the tube's extrudability. Test for rate of absorption. Rub the ointment over a specific area of skin. Serum and urine samples should be examined for the amount of drug absorbed at regular intervals. Spreadability. At the center of the glass plate, apply a sample of 1 gram of semi-solid. Carefully, place another glass plate on top of it. After 30 minutes, the semi-solid's diameter in cm is measured, 3 times of the experiment to be conducted, and the average is calculated. Uniformity of container. For products with multiple doses that have 5 grams or more, take samples from the top, middle, and bottom of a single tube. For products with multiple doses and less than 5 grams of product, test 2 more tubes from the same batch. If the product fails acceptance criteria A, then evaluate test results using acceptance criteria B. Acceptance criteria A. All assay results are within the range of 90%, 110% of product label claim. Acceptance criteria B. No assay result is outside the range of 90%, 110% of the product label claim. In vitro release test. Release through a cellophane membrane. Use a Franz diffusion cell. 100 milliliters of dissolution medium at 32 degrees Celsius was stirred for an hour at 100 revolutions per minute. Concentration versus time graph. Test of non-irritancy. 24 human volunteers are chosen for this test. For 21 days, a specific amount of ointment is applied daily to the forearm or back. Every day, the kind of pharmacological action is noted. There shouldn't be any obvious reaction, erythema, or intense erythema with edema and vesicular erosion. Metal particle test for ophthalmic ointment. Empty the entire contents of 10 separate containers into petri dishes. Heat the petri dishes for 2 hours at 85 degrees Celsius. Place the petri dishes upside down on the microscope stage. Check the entire bottom of the petri dish for metal particles and count any that are 50 micrometer or larger. The requirement is met. If there are no more than 50 particles in total across all 10 tubes, there are no more than 8 of particles in a single tube. If the requirement is not met, repeat with 20 more tubes. If there are no more than 150 particles of 50 micrometer or larger in all 30 tubes, the test is considered successful. Additionally, no single container can hold more than 3 of these particles.
Stability testing. Quality control. Stability testing of ointments and creams is an essential part of ensuring the safety, efficacy, and shelf life of these topical pharmaceutical products. These tests are conducted to evaluate the physical, chemical, and microbiological stability of ointments and creams under various storage and usage conditions. It is important to note that specific testing protocols may vary depending on the formulation and intended use of the ointments and creams. Manufacturers may develop their own customized stability testing programs to address the unique characteristics of their products. The following are some key aspects of quality control stability testing for ointments and creams. 1. Physical stability. Testing. Appearance. Assessing the visual characteristics of the product, including color, odor, and texture. Viscosity. Measuring the thickness or flow properties of the ointment or cream. pH. Determining the acidity or alkalinity of the product. Homogeneity. Checking for uniform distribution of ingredients and absence of phase separation. Emulsion. Stability. Evaluating the resistance of emulsions to creaming or coalescence. 2. Chemical stability. Testing active pharmaceutical ingredients. Assay. Quantitative analysis of the active pharmaceutical ingredient to ensure it remains within acceptable limits. Related substances. Identifying and quantifying any impurities or degradation products. Preservative assay. Verifying the concentration and effectiveness of preservatives used in the formulation. Compatibility with packaging. Assessing the impact of packaging materials on the stability of the product. 3. Microbiological stability. Testing microbial contamination, evaluating the product for the presence of bacteria, molds, and yeasts. Antimicrobial efficacy. Assessing the effectiveness of preservatives in preventing microbial growth. 4. Accelerated stability. Testing, subjecting the ointments and creams to accelerated aging conditions, such as elevated temperatures and humidity, to simulate long-term storage in a shorter time frame. Monitoring the physical and chemical properties of the product over time to determine its stability and shelf life.
In conclusion, raw material quality control in semi-solid formulations is a critical aspect of the manufacturing process, and it is vital for ensuring product safety, efficacy, and user satisfaction. By adhering to established standards and conducting thorough testing, manufacturers can deliver high-quality ointments and creams that meet the desired specifications and effectively address dermatological needs. In-process quality control testing of ointments and creams is crucial for ensuring the product's characteristics and quality. Several factors can affect the quality attributes of these topical formulations, including formulation variables and process parameters. Finished products quality control is a crucial step to ensure the finished products met all the requirements to be considered high quality, safe, and effective. Tests have been categorized into three main parts: universal, specific, and performance tests. These tests performed and validated to ensure that all criteria are met for the semi-solid to be considered accepted for packaging, labeling, and later on for distribution. If the product passes all the tests, it can be released for distribution. However, if any defects or issues are identified, corrective actions should be taken to ensure that the product meets the required quality standards. Finally, please be noted that this video was a teamwork project made by pharmacy students in the College of Pharmacy of Taibah University. Thank you for watching.